I mean, that's what this is. Okay, this is the metric topology. And then kind of continued because I already talked about what the metrics are. So a few things, if we have a subspace of topological space X with a metric D, then it's given that we have restriction of the metric D to A cross A. This is a metric for the topology. Okay, so this is the relationship between the metric topology and subspaces. And then for other things we've got, so long as we have unique points X not as Y in the metric space XD, this is a metric space, and we choose epsilon to be half of the distance between the points X and Y, then by the triangle inequality, which is given as a property of metrics, is going to yield that the ball on the metric D centered at the point X, radius epsilon, does not intersect the ball with metric D for the point Y, epsilon. So that is empty set. And so basically what this is saying is that the Hausdorff axiom is satisfied by every metric space, or by every metric topology. And then two examples is that we can have Rn and R omega metrizable. And then we will show at the end that R omega is not metrizable on the box topology. Okie dokie. So the most of what we're going to talk about is continuous functions and the metric topology. Okay, continuous functions. Continuous functions. Here's a theorem. Theorem is going to be if I let f be a map X to Y, and we're saying that X and Y are metrizable, then metrizable with metrics dx and dy respectively. Then continuity of f, continuity of the function f is equivalent to the requirement that given a point X, it will take a point X in the domain space, and then we choose a positive epsilon. Then there exists a positive delta such that the metric for the X in the domain space between the points X and Y, so long as this is less than delta, that gives that the metric in the range space y between f of x and f of y is less than epsilon. So we can prove this. And I'm going to start by choosing f to be continuous, and that's an hypothesis. Let f be continuous. And then we have to choose a point in the domain space in positive epsilon. So we'll choose, given x and epsilon, we're going to consider the set, which is going to be the inverse image. If we take the ball centered at the point f of x in the range space with epsilon back into the domain space, which is open in domain space x and contains our chosen point x. And then it contains some delta ball, given by b centered at x now in the domain space with delta, which is centered at x in the domain space. So now we have that if y is in the ball bx delta, then f of y in the range space is going to be in the ball b, which was centered at f of x with epsilon. And that is what we wanted. So now we got to do the converse equivalences. If the first is true, then the second thing. So converse of the original statement needs to go in the opposite direction. Let's see, can I fit the converse? I'll just erase it and I'll do the converse. The converse thing. We're going to now suppose that, so this condition that if I choose a point in x with a positive epsilon, the existence of delta being where the metric between x and y in the domain space being less than delta is going to give that the metric between the points f of x and f of y in the range space will be less than epsilon. That is what we'll call the epsilon delta condition. So suppose that the epsilon delta condition is satisfied because we're going in the opposite direction. Satisfied, and this being satisfied in converse is going to give the continuity of f. And topologically, we just need for an open set, we need its inverse image to be open in the domain space. So let V be open in Y. And as a quick background, the way that we want to show continuity, or at least definition, is if you choose an open set in the range space, then give the inverse image to be open in the domain space, and that's equivalent to continuity. So that's what we want to show. So let x be in the inverse image of the open set B and Y. And since we have that f of x is going to be in V by the way we've chosen it, and that means there's going to exist a ball centered at the point f of x with epsilon, which is a subset of the open set V that we had. So it doesn't have to be the entire thing, but it could. And then by the epsilon delta condition that we're assuming in the converse direction, then we have the existence of a ball centered at x with delta, such that the image of the ball, so under f, image of the ball x delta under f is going to be a subset of the ball that contains the point f of x, which is the image of the point x with epsilon in the range space, which makes the ball bx delta a neighborhood is a neighborhood of the point X contained in the inverse image. In the inverse image of V, and that's going to make the inverse image of the open set in the range space open in X, and then that's what we wanted to show for continuity as desired. Cool. So continuity is given by the epsilon delta. So epsilon delta out of the reals. And if you were to apply the metric on reals, then this difference is essentially the absolute value, the difference between x minus y less than delta is giving the f of x. So I'll write that real quick. This generalizes epsilon delta that you would have learned in, or at least seen the result one at least. So I can have basically for all x in the domain, we'll call that x still. Choose a positive epsilon, then you're continuous. And if you have a positive delta, where the metric, this metric dx in the range, because we're using real to real value functions, so f is r to r, then you can have this minus y being the delta. That's what's giving you, and then you use the same exact metric, but since we're using reals between f of x and y, f of x minus f of y by n epsilon. So this version of continuity is an application of this theorem.
Could you maybe give an example with a different the taxi cab metric?
No, let me see what I have in mind. I know I did an example. I do the box topology.
Okay, is that the
Yeah, that's the one that's the same as product topology on finite products.
equivalent continuity of the box topology?
Yeah, that's the at the very end, because it basically goes to show that R omega is not metrizable. Yeah,
That's good enough.
so I'll try to get to that before time. The lemma that we're going to use later, called the sequence lemma. And it's going to go, we're going to let X be a topological space. And then we're going to choose a subset A of the space X. And the lemma is going to basically say that there exists, well, if there exists a sequence of points X and that is in the subset A. So a sequence of points in our subset A such that it converges to a point X. And that means that X is not necessarily in the subset A itself, but X will be in the closure of A. And also, the converse is true if A is metrizable. So if we have A metrizable, and we have a point in the closure of A, then we're guaranteed the existence of a sequence of points in the subset A that converges to the point X. So we can suppose that we have a sequence in A that converges to the point X. And then every neighborhood U of the point X must contain a point of the subset A. So by definition, X will be in the closure of A. And then conversely, we're going to suppose that A is metrizable, and also that we have a point in the closure of A. If we let D be a metric for the topology of X, G of X, for all positive integers n, we're going to take the neighborhood BD for X and 1 over n, and choose the sequence xn to be a point, maybe a point of its intersection with the subset A. And then we assert that the sequence converges to X. So any open set U containing X contains an epsilon ball, B D X epsilon. And if we choose sufficient n, so that n is going to be 1 over n is less than epsilon, then each xi in the sequence xn is going to be in the neighborhood U for all indices I that exceed the sufficiently large n. And then there's a theorem that is structured in analogous form to sequence lemma, which is actually what we use for function convergence. That theorem is going to start, instead of this point x in the topological space, we start with a map f taking x to y. And if the function f is continuous, then for every convergent sequence, so every convergent sequence of points xn that goes to x in the domain space x, the sequence that is f of xn. So the function values, we have the sequence xn. So we're basically sticking the sequence inside of a map that's spitting points out in y. This converges to f of x in y. And the converse, again, holds if we have y being vectorizable. So the converse holds in our space x is vectorizable. So moreover, if I take xn, and this is a sequence in x, and I'm going to say that this sequence is going to converge to the point x. That's going to give that the function values, this is a sequence. So I know it doesn't look like a sequence. We use this notation though. The subscripted n is implying that this is like a point, like x1, x2, x3, x4, x5. And now we're just taking those set of points and then whatever is the essentially image of the sequence in the after you map it into the function. And this is going to converge, and that's pretty intuitive, right? So if xn is going to converge to x, then the image of this should converge to the image of what it would converge to. So then this is going to exist in the range, which is then converging to the image of the points that it converges to. And then the other way is true because we could go backwards. If I start with x being metrizable, which is a stronger condition, and I take a sequence of points given by the map x and y, f of x and converges to x, then that guarantees the existence of the sequence xn to n x. So xn x. We're almost ready to show that addition is continuous. And the four operations are continuous. I don't remember if I taught you guys the binary operations were not. Okay. Operations of continuity properties. So these are the kinds of things that you're going to have textbooks tell you, well, there are proofs of these things, but not now. So here's now. First thing we need a lemma. And it's essentially that plus minus time. You know what I should do this before I do this? As background, a binary operation is basically going to be it's a type of function. So if I take what we will, if I have a set S and I have elements inside of the set S, and then I want to put a binary operation on it, so some sort of operation on it, then what I'm really saying is that I've defined a map that's going to take elements of S cross S and then map that into just the set itself. So I choose an element that's in the set, I choose another element in the set, they interact via the operation and it spits out something else. Okay, and so the way we would represent, so in the same way that I want you to think of like f x to y, and then you notate f of x is equal to y. Well, here, if you were to do the same thing, ignoring the fact that the symbols look funny, you get star of, and then what constitutes these coordinates? Well, it's going to be some a and b, where a and b are in S, is going to be equal to some whatever it spits out. And whenever you do the notation like this, you can either choose to double parentheses it or not. So if I really want to emphasize that these are ordered pairs, I could say star of an ordered pair A and B is what we really mean as a map whenever we have the operation listed between two things. So A star B is really saying take the ordered pair AB and see what it maps to under the map star in the particular set S, assuming that A and B are in S. And if these elements are required to be in the set, so that's why your closure is important for us. So when we do addition on real numbers, what we're really talking about is, so now that S is no longer arbitrary, let's choose R. And then instead of star, let's actually choose just regular addition. And so what I'm saying is, okay, I take plus and I map ordered pair of two real numbers because I'm adding two real numbers together. And then I want to spit out a real number, right? If I add two real numbers, I want to end it with a real number. So if I have some x and y that are real numbers, then I can say that x plus y is actually the element plus it's the image of the ordered pair x and y under the map plus for real numbers. So this is going to be helpful to see when we talk about continuity for functions being added together as things. So this is binary operations. this will make a little bit more sense. So the lemma is going to say plus. So now when you see this operation, I'm referencing the actual math. So this is plus, which is taking r cross r to r, and then minus and multiplication. These are three maps, and they are continuous functions. So are continuous functions. And it's weird to think of addition as a continuous function because you think of a function like a parabola or something like that. But these are operations, are functions. And these are from r cross r into r. And then why did I separate out division? Why might you think I separated out division? Yeah. So, but we can fix that pretty quickly. We can basically just say that for division, this particular map, what I'm going to require is essentially the first number. You can do 0 divided by x, but you can't do x divided by 0. So if we're representing the product of what you're allowed to do, is division commutative? Can you change the order of division? No, and that's okay, because given so long as we have the order of the product right, we can actually have a more full picture of division. So division is a continuous function from. So we can have 0 as the first thing you divide by, but you can't divide by 0. So what we do with this little asterisk means take this set, all of the non-zero elements of that set. And then that is going to be mapped to a real number. So division can be continuous. We just have to change basically the definition of its map to make it work. And then now we can prove that if let's see, do I want to prove that? Yeah, I'll prove this one. If X is a topological space, and if you're given now maps F and G, so F and G are both going to take a set X into real numbers, they're real, somewhat real value. These are continuous functions. Then F plus G, F minus G, F times G, and F divided by G. Well, I'll separate out F divided by G because it gets interested. And these three are continuous. And then we'll leave the modification to G of X. So long as G of X is non-zero for all X on its domain, then we are also going to have F divided by G is continuous. So all the times that you're able to say, so if I took something like F of X is equal to sine X, and G of X is equal to X squared plus 2x. Continuous on the domain, because each of these maps are real valued functions. That is, what we're doing is both F and G are taking the set of real numbers and mapping into the set of real numbers. So continuous, continuous. And so what we're saying is that this theorem says that F of X plus G of X, which is equal to sine X plus X squared plus 2x, will also be continuous. So the map F plus G, mapping R to R, is also continuous. We use this all the time, and you really can't do any calculus at the engineering level without assuming this to be true. But we're actually going to prove it. And the proof is it's actually really nice when you get the binary operation notation. So the textbook that I was studying from basically said, well, it's kind of obvious, but I found a really neat way to represent it. That uses essentially the ingredients from the theorem. So if I take this proof, I first need continuous F and G X star. So let f and g. Take x into R, and then this is continuous. Continuous. What we're going to do is we're going to define another map with respect to the stuff that we're assuming to be continuous. Because what we do have is that composites are continuous. So if you have two continuous functions, then the composite's continuous. So we define H to be a map that takes some set X over to R cross R. And then by any value H of X is going to be given by the ordered pair F of X and G of X. So this notation, when you use that cross symbol in between, is essentially indicating an ordered pair. So I could have also written this as like ordered pair F of X is the first coordinate, G of X is the second coordinate. And we'll use that in a second. And so H gets its continuity. So H gets its continuity because product those product projections. This is a different theorem from like 3 sections ago. So I'll just say we see that H is continuous. And if addition is defined by plus, which takes R cross R to R, like we talked about just a few minutes ago, then here's how we can run it down. So we're trying to say that if I have two separate functions, f and g, and if they're continuous, then their sum, I can take f and add g, and it's still going to be continuous. So f plus g. But addition, this is representing that these are the elements in the ordered pair, and then we're spitting this out. So we have the function plus, and these are the ordered pairs. We have f and g. But we just defined H as a continuous map whose outputs essentially are R cross R. There's these ordered pairs, F and G. So what we've done is F plus G is really plus F of G, or plus F comma G, which is H. So this is the function H being composed in the function addition. So this is plus of H. And then since this is continuous, so continuity of plus and H independently gives continuity of the composites, and moreover, that is F plus T is continuous. And so you could make similar arguments for subtraction and a very similar argument for multiplication. So it's basically you would just copy and paste the reasoning over and over again, and then you'd make a slight modification to the domain for division. So you can add, subtract, and multiply real value functions together, and they're continuous from the original function. Okay. Okay. Here's a look like this. We'll define uniform convergence, and then prove the uniform limit. Well, no, we won't prove that one, but we'll do examples with the box topology, and then also uncountable products of R. So let f sub n taking x to y be a sequence of functions from the set X to the metric space Y, and then D is the metric for Y, so let D be the metric for Y, and we say that the sequence f of sub n converges uniformly to the function f x to y if given positive epsilon, then there's going to exist a integer n where the distance between fn of x and what you're converging to is going to be less than epsilon. For a certain point past a sufficiently large n, for all n greater than n and all points x. Fun fact, I had to figure out what this was on the spot in somebody's Calculus 4 final exam last year. Scared me. We didn't talk about this in class, by the way. When I went to that final, never saw that definition in my life. It's obvious when I can't remember. Did I actually end up getting that question right? I'd have to look back. I'm pretty sure I got this one right. Yeah. Well, because so the way I would study for that class is we didn't really know. We knew generally which theorems to know, and there were certain things you just had to be able to prove something. So I memorized. There was a 48-hour window, where I had memorized almost page for page, like 6 chapters of that calculus book, and I almost vomited after that because it hurt. So uniform limit. The sad part is that after all of that, I actually technically never got to uniform convergence. So I still had to figure that out on the exam. That was annoying. Okay. So uniform limit theorem is going to say if I've got a sequence of maps x to y, and the sequence of continuous functions. So we require the maps Fn to be continuous. And then before we would just define a set X, but now we require structure of having a topology on X for this theorem. From the topological space X to the metric space Y. So if the sequence f of n converges uniformly to f, then f is also continuous. A silly way I like to think of this is like this is massively abstract squeeze theorem, but not quite. But the intuition behind what's going on here, essentially all of these separate sequences that are going on, and then they're all converging into one continuous function from a bunch of other continuous functions, and eventually settles into the continuous map. So let's talk about some examples, some computations. And we'll feature the box topology because it was, I think I talked about it would break down with infinite sizes of products. So that's why it was different. Well, the box topology doesn't break down, but it stops becoming equivalent to the product topology, which doesn't break. So just as a, so that you guys know what's going on. This is a scalar. You guys have seen this because we've talked about that. Okay, R2. Wow. Then elements in R2 are going to essentially be vectors with how many components?
Sure.
Yeah. So that's when we're talking about something like you have x1, x2, right? And then if I have R3, which is calculus 3, so that's all we're doing, what is this going to look like? Yeah. So x1, x2, x3. Now there's different ways you can blow this up to infinity. So I could say I want an arbitrary size. So if I said a finite arbitrary size Rn, so n can be as big as you want it to be, but it's still technically you're fixing a constant. So it's going to be, as the way we represent this is we start at x1 and then the ellipse is up to xn. It's going to indicate that size of a tuple. So that's a real value tuple. And then the difference between Rn, and I think I wrote this on the board earlier and I forgot to explain it. R omega. Omega is the last letter of the Greek alphabet to kind of indicate this unendingness. So this is going to be, imagine now, instead of just choosing a number, even in its generality, this is going to be that section of integers is now just taking as the entire set of positive integers. So it's going to be all the way up. Not an uncountable infinity, but the 1, 2, 3, 4, 5, 6, 7, 8, all the way up. So this is going to be represented as x1, x2, ... And that's going to indicate that goes on all the way, where 1, 2, et cetera, it's going to go up to all the positive integers. Okay. So this is what we're talking about in the example. This is where the box topology breaks. And we can use the sequence number to show that. So R omega in the box topology is not symmetrizable. Not symmetrizable. There's no way we can impose basically a metric that satisfies all of the properties necessary for it to be in metric space on R omega with box topology. There's other ways to do it, but box topology specifically is not going to work. So we can, I called it a computation. That's kind of misleading. It's not going to look like a computation. But the sequence lemma does not hold. Does not hold for R omega. And this is basically our way of getting it to not be metrizable through the conditions in sequence lemma. So if I'm going to have some set A, and we'll define this as x1, whoops, I was going to do Rn there. x1, x2. So it's such that each of the xi, so each coordinate, is we're going to take only the positive coordinates here for all indices plus. This by definition is a subset, a proper subset of R omega. And now you should be, you guys know what this is, zero vector, and we understand this to be in the context of R omega, unending tuple of infinite zeros. A 0 at every coordinate. So every xi equals 0 for all I integers plus. And this is in the closure of A, because if I take B to be the basis element, A1, B1, and then A2, B2, essentially this is in that box, you're creating these little rectangular boxes ad infinitum, then if this contains our zero vector, then the intersection between the basis element and A would not be empty because we would have the zero. But we have a problem because there does not exist a sequence of vectors an that are in the set A or the subset A such that an converges to a zero vector. And if we let a n define it to be x, so I'm going to take 1n and then 2n, etc. So the part that's getting counted up, so if this is like mn, then m is going to go up with integers and n is fixed. What we choose. We still want all positive valued coordinates. Then the basis element for the box topology specifically, box topology. And we call this a different one, so let's do b prime minus x11 x11. So all of these intervals that are going to go between and all the way through the positive integers. So now it's minus x22 and then x22, and then it would go minus x33, etc., etc. So we find those boxes, that basis element. This also contains the zero factor, but does not contain an element of the sequence that we have, element of our sequence A, which means that this sequence AN is not in B prime because each of these x and n is not found in the intervals minus x and n, x and n. That is, the box topology allows you to choose a basis element that's going to have exclude the sequence points from the basis elements. So you can get something that includes the point that's supposed to be in the closure without there being existing a sequence that gets you to the point in the closure, which contradicts the sequence lemma, so it's not metrizable. So I can summarize that here. So the sequence A sub n not going to go in the box. The box. So that's how this is a completely different metric. Okay. And then last thing. R omega is what we would consider an uncountable product of R's because infinite, but it's a mistake to think of automatically assume uncountable with infinity. Because infinite sizes can be countable. So use sections of the positive integers and positive integers are countable. And there is a correlation between dense sets and countability, but that's analysis, not today. And uncountable product. So the reason why it's uncountable and not just omega is because that size of infinity is not the only size of infinity that there could be. So you could take the card if you decided to take the size, the number of all of the real numbers instead of the size of the positive integers, which would be the same as just integers, but it's uncountable. Either way, it's a size of infinity, and you can't find a bijection between a section of positive integers, which would give 1 to n, and that's how we're defining that. Of R with itself is not metrizable. And so the way we kind of represent these tuples more abstractly. So if I want to take something uncountable, so I'm going to make an indexing set J. So J is my indexing set, and I'm going to let this have whatever size I want it to be. So this could be any size that's possible. And if I'm talking about products of R with itself, then I'm looking at Rj instead of Rn. And the difference between Rj and Rn is when we did Rn, n is technically a number. So you could have elements that look like x1 up to x, and that gives you a description of tuples, whereas here, J is now a completely different set. So if I index over a set, I can do an example of that. So if I have an index set that's not even numerical, because you think of when you index something like I is equal to 0, 1, 2, 3, 4, you don't have to do that. You can index over whatever you want. So I can index over alpha, beta, gamma, delta. Non-numerical, but this is the set of objects that I want to index over. And then if I take another set, so maybe I take some set X, and this is the thing that I'm taking products with, then this xj is going to look at x alpha, or no, not really that. If I tell it this Rn, yeah, I'm pretty sure it would be x alpha, and then x beta, x gamma, x delta, where the set X is going to have some sort of set of elements for each one of these X alpha. So then, yeah, you can do that with real numbers and not just J. But, okay. Let's stay on data. Thank you, Dr. Lang, for letting me do this direct study. I've been doing the topology study on my own, but then we get together on Tuesdays and then have math chat. So I get to have credit for doing random stuff in mathematics, and we get to talk about mathematics. So I'm going to be doing algebraic topology. This is more point set topology, really. So algebraic topology is going to be next semester. Probably keep it at the same time, right? If that works for you. Cool. All right, thanks, guys.
Open, if anybody